Okay, so in this tutorial we're going to continue looking at the motion of a fan cart, which we established the other day to be accelerated. So we want to look at two different types of graphs that are telling the same thing. We want to be able to interpret them, and then we want to be able to do some analysis on them, namely looking at slope, and in the process we will introduce a new quantity that measures motion, something we're familiar with called acceleration, but as it turns out it's a little bit more involved than most of us realize. So we're going to take our time with this. Stop the video when you need to process some information, and then we'll discuss more in class. Okay, so as we saw with the fan cart, when you look at its position versus time, something's going up. That's clearly it's where it is. Okay, so it goes from 0 to 50 meters in 10 seconds. However, the shape of that curve is not a straight line. And so we already know that a straight line indicates a constant rate of change of position or a constant speed. All right, here is a velocity time graph that shows that its speed is steadily increasing. Okay, it's going from 0 to 10 meters per second, and it takes about 10-second times. So let's understand, or let's look at what we can pick up from each of these graphs. Alright, so the first thing is, how do we interpret conceptually what's going on position time? Yes, we can say it's speeding up, we can even say it's accelerating, but let's look at it just in terms of position. So what we can see as time increases, position is clearly increasing. Right, that's not a surprise. Alright, let's try that again. I need a bigger space here. Okay, so position is increasing. Alright, now what's less obvious is how is it increasing. So because of the upward concavity of this parabola, we can say it's increasing at an increasing rate. Okay, so something's increasing, its position, something else is increasing, the rate at which it's increasing. In other words, for every given interval of time, if I go over 2 seconds, we see that it's only gone a little bit of a distance. If I go over another 2 seconds, it's covered even more ground in the vertical direction, and then we see even greater distance, and so on and so forth. So if we were to have dots, they would be getting further and further and further apart. Okay, so increasing and increasing rate, in other words, the speed is increasing. Alright, so we already know that. Now let's look at the velocity time graph. Again, when we look at it, we can see something's going up. Alright, so it's not positions per se, because we can't see position directly, but we see that the velocity is increasing. I'm having trouble with the pen today. Alright, now what's the line tell us? Well, the rate at which it's increasing is constant. So it's increasing at a constant. Try a different approach here. Rate. Okay, so let's contrast these two ideas. Increasing at an increasing rate. So the actual points are getting further and further away, and the slope is increasing with time. Whereas this one, we're increasing, the points are getting further and further away from 0, but the slope is constant. Alright, so let's talk about the slope of this graph. If we were to take the change here and the change here, we'd see that this vertical part represents the change in how fast we're going, and of course the horizontal part is the change in time. So the slope is really this divided by that, delta v over delta t, which means that it represents the rate, because the t is in the bottom, of change of velocity. Okay, and the rate of change of velocity is called acceleration. Oops. Okay, so to accelerate means to change your velocity. And to change your velocity can mean three things, which we'll discuss at a later time. But for right now, let's mention it. When we hear acceleration, we automatically assume we're going faster. And that could be true. But you could also be slowing down. That's a change in your velocity. Note we're not saying change in speed, so what's the difference between speed and velocity? Well, velocity takes into account direction. So to accelerate could also mean changing direction. Okay, so we'll talk more about that in another lesson, but keep that in mind for now. So based on that slope, we can define acceleration equation-wise. We can say A is delta V all over t, and delta V is the change in velocity, which means it's final velocity minus initial velocity divided by time. Okay, so VF minus V sub I all over t, and this is found in your reference tables. I believe this is the second equation in your reference tables. So when we do acceleration, right, if we were to do change in velocity over change in time, as we saw also with the fan cart, that we're dividing meters per second, that's the change in velocity, divided by time, gives us meters per second, or that can be written as meters per second squared. Okay, so what that means is if we have an acceleration here, so we'll look at this in a few seconds. For every second that goes by, the vehicle is going a certain number of meters per second faster or slower. And we'll see how this is important later. Acceleration is a vector. Okay. So you can have negative acceleration, you can have positive acceleration, you can have sideways acceleration. We'll look at the first two in more detail later, and then eventually we'll look at sideways. Okay, so let's just do a quick example to finish up this little lesson. So I have two graphs that are showing the exact same thing, and I want to find four things. What is the position at a given time, in this case 6 seconds? How fast is it going on average? What's its instantaneous velocity? In other words, the speed at the 6th second. And what's the acceleration A? Okay, so how are we going to find where it is? Well, that's pretty straightforward. We're just going to we're going to read literally, we're not going to do any analysis, the position time graph. Okay, so if we go up to here, and let's erase this, okay, and we go over to the 6th second, and we go up, and we go over. I think that's trying to tell us, well, I don't know if I read that exactly correctly. I believe that's at the 18th meter. We've gone 18 meters in those 6 seconds. Okay, next question asks how fast we moved on average. Well, we might want to go to the velocity time graph. After 6 seconds, we see that we're going 6 meters per second, but that's what we're doing at that instant. So that's actually our third one. We'll come back to that. So on average, we can actually do one of two things. We can say we started at 0, we finished at 6, so on average we went 3. Or we can use the idea that we've already learned, and that average velocity is, by definition, distance, total distance divided by time. So if we go over to this graph, at 6 seconds we went 18 meters, so V average is going to be 18 meters divided by 6 seconds, so 3 meters per second. And if you think about what we said before, we went from 0 to 6 meters per second in that time, the average would be 3 as well. Okay, well, we'll get that later on. All right, instantaneous velocity, we've already done that. That can be read directly from the VT graph. Oh, my writing's getting worse. Okay, so we've already said that. After 6 seconds, how fast are we going? We're going 6 meters per second. Alright, and lastly, what is our acceleration during this interval? We can do that from the equation, which is really just the slope of the VT graph. Okay, so if we go and look at that, after 6 seconds, we already know that we've gone from, let's get rid of that, we've gone from 0 to 6 meters per second, right? So there's our point right there. So that's going to be, spacing's just off a little bit, 6 minus 0 meters per second divided by 6 seconds, and that means we were accelerating at 1 meter per second per second. So every second that's gone by, we're going to be going 6 meters per second faster. Whereas this graph is telling us that our average speed for the first 6 seconds, which means for every second that's gone by, on average, we went 3 meters. Okay, so 18 meters overall. Now that does not mean we went 3 meters each interval, because we already know from our dots that they're getting successfully further and further apart. So the first interval might have been 1 meter, then 2 meters, then 3 meters, then 4 meters, then 5 meters, then 6 meters. If you add that up, you get something close to 18. Right? It'll be pretty close, but that's the idea. Okay, so to review, when you're changing speed, you're accelerating. That can mean speed up, slow down. When you're changing velocity, that also includes the possibility of changing direction. We can see changing velocity by a curve. In this particular case, our slope is getting steeper and steeper, so we can say we're going faster. And then we can look at this graph, the velocity time graph, which shows that our velocity is going up, but at a constant rate. In other words, our acceleration is constant the entire time, even though our velocity is increasing and our position is increasing. In the next tutorial, we'll look at how to other details from these two type of graphs and other analysis that we can do.